Today we are very fortunate to have Dr. Laura Waters here from Sonoma State. She had her undergrad at Juniata College. Juniata College, and then went on to the University of Michigan for her PhD, and did a postdoc in the Smithsonian in Washington, D.C., and has since been at Sonoma State for about a year now, a little over a year. So we're very fortunate to have her here. She drove over here and saw all the beautiful orchards that makes up this part of the valley, which is a big surprise for her, and also all the billion-dollar agricultural industry here. But we're going to talk about the source of all that beautiful sediments in the volcano. So with that, I give you Dr. Laura Waters.
For sediments. How dare you?
Oh
my gosh. Okay, what kind of welcome is this? So today, I want to talk to you guys about a paper that I had come out last year, and this was in geology. So if you want to read more about it, you can find it there. And this is basically sort of a big conclusion that came out of a really long period of work. And the title, Why Obsidians Why Obsidians Erupt and Aplites Freeze, is basically a function of crystallization kinetics in high silica melts. And so high silica melts mean rhyolites. And a second title, well, I first want to acknowledge my PhD advisor. And so I was well out of my PhD when we decided to write this paper together, but we just had a great working relationship. And so she's just a huge part of this talk, too. So the second title I was thinking about working with is why doesn't continental crust evolve to its fullest potential? So this is really different than the first title, but these two things are actually related. What's controlling the eruption of rhyolites and what's controlling the differentiation of continental crust are in fact related. And so I want to convince you of that today. So can anybody tell me what continental crust is made of? No? Any ideas? Where would you go to see?
High silica content.
So it is enriched with silica relative to oceanic crust. So if I were asking this question, I would go to areas on Earth where continental crust is exposed. So California has a great exposure of the upper crust in Yosemite. And if we were to go there and measure all the rocks, we would find that those rocks raise the silica content from 60 to 72 weight percent. So that's not quite high silica, right, when we think of the entire range of compositions that magmas could be on Earth. But it's still high silica and higher in silica than oceanic crust. Another place that we could go and look inside of a continent is a place like the Khoestan Arc. Now this is a place where an island arc has been smashed into a continent and turned on its side, so that when you walk across the surface, you're actually walking through a crustal section. And if we measured all the rocks there, we would find that the composition of this island arc, or the lower crust, is 50 to 58 weight percent silica. So this is a little bit more mafic. The third way we can tell what a continent is made of is by examining glacial tilts. And so glaciers sort of move over the landscape, and because of their conveyor belt-like action, they break up all the rocks over which they traverse, and they essentially average all of the rocks. And so if you measure the composition of a till, it'll give you a pretty good idea of all of the compositions of all the rocks that that glacier went over. So the final way we can sort of look inside of a continent is to do seismic. And so here are results of a seismic study by Christensen and Mooney in 1995. And I'm showing the results sort of warm going to cold colors, and that's showing seismic velocity. And so faster velocities are down here in the cool colors, and they're correlated with denser rocks, which is also correlated with silica content. And this is essentially what continental crust is. We have a landmass that's segregated based on composition, right? So we have a stratification based on silica content. And in order to get this, we need an igneous process called differentiation. So when we talk about differentiation, we can talk about a geochemical perspective, in which case we're talking about the evolution of the interstitial melt. So this could be achieved by partial melting or crystallization. So we're talking about the interstitial melt getting enriched in silica. But it's not just that, right? We've formed layers. So what else has to happen? That interstitial melt has to escape the crystals and become a new layer. So we also need some sort of a mechanical process. So that interstitial melt needs to segregate out. Now here's some just options. You can use volatiles to sort of exsolve it, just like if you crack the soda too fast. There's tectonic, right? You can shear it, compress it out, or maybe you have some pressure gradient. So these are all different things we think about when we're talking about how do you develop a stratified continental section. For this talk, if I ever say the word differentiation, I just want to be clear, I'm talking about both of these things. How do we get rocks that are enriched in silica and forming new layers in the earth? So that's sort of what I'm going to tell you about today. And it's funny because I told you I was going to talk about Obsidians and Aplites, right? So we're not even there yet. So if we were to just sort of assign rock compositions to these different layers, we might assign dacite to the upper crust, andesites to the middle, and basalt and basaltic andesites to the bottom. What are we missing? Anybody know? Rhyolites. Yeah, I heard it. I heard the R. Gentle R, soft R. It's okay. Yeah, so we're missing rhyolites. And so here we have this continent where we have something happening to make this stratification, right? This is across the earth. This is a global compilation of arcs. So this is globally, right? So we have this differentiation mechanism that's happening to drive the segregation of andesites, the segregation, but something's stopping it. And so that's actually what's going to control whether or not a liquid erupts or whether or not it gets stuck in the crust. And so what you notice is that the upper crust is enriched in silica, but there's nothing equivalent in composition to high silica rhyolites. So high silica rhyolites, so this is my expertise. This is sort of what I focused on for many years. And so I just wanted to show you what they are. So this, when I say this, I'm talking about liquids that have 75 to 78 weight percent silica. So this is super silicic. I know that some of your field courses go down to Bishop, California. Has anybody participated on that before or been down there? No? Yeah? Okay, great. So you guys might have seen some of these examples. So we have the Huckleberry Ridge tuff. This is a highly differentiated rhyolite. The Lava Creek tuff, the Bishop tuff. Now, this is our California tuff. That's really great. You might see that sometime. The volumes are enormous, right? 2,500 cubic kilometers. Those are huge volumes. So it's not like these liquids occur in such tiny volumes that they can't form a new layer in a continent. So the question is, if we do get rhyolites that are enormous, why don't we see them forming layers in the earth? This is our mystery. So if where we do get where we form the stratification on Earth is in subduction zones. And so one question we can ask is, if continents don't have this high silica-rich layer, do subduction zones actually erupt this high silica layer? So in this paper by Wes Hildreth, he did a survey of all of these different volcanoes. So here's Lassen, this is you guys' volcano. And he took an inventory of all the rocks that are up there, and he commented specifically in text, high silica rhyolite is especially rare. So here we have a subduction zone where we're making our stratified continental crust, and we're missing the rhyolite. And he notes that it's limited to 3 rear arc extensional fields. So this would be your Medicine Lake. It's a one-off. It's not common. If we look at this in a different way, instead of leaning west, if we go look at the data, here's a histogram, so weight percent silica, of whole rock analyses from the Cascades. And what you can see is Wes is right. So over here, this is our high silica rhyolites, right? 75 to 78 weight percent silica. They're missing. And so that suggests that there's some process at subduction zones where continental crust gets stratified that's sort of holding these liquids back. The last place I kind of want to show you, like you're getting the picture, is the Altiplano Puna. So this is the thickest crust on Earth where we've had volcanism for 10 million years. And if you look at the relative volume of the rocks erupted there, they're always intermediate and very rarely making it into this field. So 10 million years. How long does it take to differentiate? How long would it take to make a rhyolite, right? 10 million years doesn't appear to be long enough. So what I'm looking at here when I'm comparing Aplites and Obsidian is I'm actually investigating why continental crust is so differentiated, but it's not differentiated to its fullest potential. Another way we could phrase that is, why is rhyolite so sparse at subduction zones? is not to say that you don't get high silica rocks at subduction zones. So high silica rhyolite does occur in batholiths, but only as scattered aplite dikes. Has anybody been up to the Tuolumne or anywhere in Yosemite? Yeah, I don't know if there's, I know you guys have your own Pluton. I was told about the Pluton, very exciting. Have you, I'm excited, man. We have like wine. I don't know. Like lots of driving. So these sugary white veins, these are called aplite dikes. And so you might have seen these when you're driving. You know, maybe all your friends are freaking out in the back as you're looking at the outcrop. But what you'll see, you see these like lovely granitoid, and then you have these stringers that go through. And so these sugary white dikes are aplites. And they have that composition we're talking about. So this is the only time you see these in subduction zone related rocks. So in 2008, Alan Glazner in North Carolina, he looked at some of these dikes and monitored their rare earth element fingerprints. So here are rare earth elements, and this is the concentration of the sample normalized to a standard value. And this is hundreds and hundreds of different samples. So anything in these dark colors, reds, blues, and blacks, these are erupted rocks, okay? And so this would be like your Bishop Tuff, your Yellowstone, and you notice they kind of look like a bird shape, right? They look like a seagull. And the Sierra and Aplites, by comparison, have this scallop shape. And so what was really important is that even though the aplite dikes have a composition that looks like a high silica rhyolite, they're not actually the same thing. And what Alan found is that these aplite dikes were forming, and this signature means that these aplite dikes are actually segregating out of, or separating out of this granitoid Pluton. So the aplites are actually coming from the rocks that are really close to them, but they never erupt, right? So if the aplites erupted, you would see this scallop shape in the rare earth element patterns in these erupted rocks. So you don't see it. It's missing from our volcanic record. So why don't they erupt? So part of this has to do with composition. So I'm going to show you some geochemical data. So this is the composition of the average Yosemite aplite dike. And what you see, I have in the red, don't be too worried, they're enriched in silica, aluminum, sodium, potassium, right? And there's not much else in them. And mostly 4 components. And what this composition is a near minimum melt. And I'll explain what I mean by that. But before I go on to the next slide, what mineral does this look like? I heard that some of you might have been in mineralogy. What? Oh no, too much? No? Okay.
Too much.
Too much. All right. Sorry. So this looks a lot like albite and orthoclase, right? So here's just a phase diagram, and I apologize if this is bringing anything back for people or causing trauma. But there's a special position on this diagram. So this is composition. This is your minimum composition, right where that star is. And then here's temperature. What happens at that star? So beneath the star, we're all solid. Above the star, we're all liquid. At that single position, all you need is a single degree Celsius of heating, and you go from 100% solid to 100% liquid. Do another way, if we brought it down 1 degree, you go from 100% liquid to 100% solid. Do you guys agree? So above there, you're liquid. Below the star, this is what we call a minimum. And so minimum melts have this property where all it takes is a single degree Celsius of heating to turn 100% liquid, or a single degree C of Celsius to just cool and solidify completely. If we were to, so this is idealized, right? Rocks aren't like this. We have a lot of other stuff in there. We could map this out across temperature pressure space. So this line right here is that minimum, but at different conditions. And like I said, rocks also have other stuff in them, right? Calcium and iron, which is why I call them near minimum melts. And the effect of this calcium and iron is to cause a little window to appear between the solidus, below this line everything's solid, and the liquidus, above this line everything's melt. And so for this type of composition, for the aplites, a small change in either temperature or pressure should do what? What do you think? What will happen if we cooled this off just a little bit? It's going to freeze. Yeah, it's absolutely going to freeze. So for the aplite composition, if they cool, maybe 5, maybe 10 degrees C, they should completely crystallize. So one of the hypotheses I want to pose to you is that maybe the Aplite dikes are freezing into place when they segregate from their source. Now this is a compositional thing. Not all rocks do this. But sort of a problem with this idea is that there are abundant examples of high silica rhyolites with the same exact composition as an aplite that make it up and in large volumes. So here's the Bishop Tuff airfall, right? This is a person. And so that's a huge thickness of high silica rhyolite that made it out. So back to the original title, what enables some rhyolites to freeze and some to escape? So it could be differences in intensive variables, could be differences in speed of eruption versus the speed it takes to crystallize. And so by comparing an aplite, something that we know is freezing in the earth, with something that erupts, we can start to answer this question. So I've told you what my freezing example is. My erupting example, I want to use the Glass Mountain rhyolite. So here's the Long Valley caldera, and this was the hole left when the Bishop Tuff erupted. Here's the Bishop Tuff in that gray color. And then here, there's this little guy called Glass Mountain, and this is 100 cubic kilometers of obsidian lava that erupted over a period of about 2 million years. And this fits our criteria for high silica rhyolite, 77% silica. And here's a picture of what it looks like in hand samples. So this is obsidian. There are large crystals of quartz, sanity, and pelagic glaze. Has anybody seen obsidian before? Exciting? Good. Stats. We've all had one or two. All right. So, but in addition to these three main phenocryst phases, we have magnetite, ilmenite, zircon, apatite. So this is a lot of crystals. But surprisingly, this thing has less than 3% overall crystallinity, which is remarkable to have that many phenocryst phases, but less than 3% crystals. And what this tells us about this particular sample is that these obsidians were once a liquid. To be this crystal poor, for geology, in a world that's full of crystals and very little melt, to have something that has less than 3% crystals and mostly glass, that tells me that this is a liquid. So this is a great sample to compare. So here again are our compositions. And I just want to show you this, not so you remember that Aplite dikes have 0.8% titanium, but that you can see the similarities. So they have very similar silica contents, they have very similar aluminum contents, similar sodium contents, and we have a little bit of a difference in the potassium, but not much. So these are about identical liquids. One of the hypotheses that we found in the literature is that these rocks erupted because they were just hotter. Maybe they were hotter, and it was harder to crystallize. It makes a lot of sense. So we can test that. If we use a zircon saturation zircon saturation thermometer, so this is based on the amount of zirconium in the sample and the presence of zircon crystals, we find that the Aplite dikes have a common temperature of about 710 degrees. That's pretty chilly for a magma on Earth. And if we apply an iron titanium oxide, so this would be ilmenite magnetite, or minerals, to compositions from the Glass Mountain obsidians, you see that their temperatures are also quite cold. So by testing these two temperature ideas, we can eliminate this hypothesis. It doesn't have to do with temperature. So that leaves the other hypothesis, which is that something is happening with respect to how fast they're erupting and the time it takes to crystallize. So I just want to make an inventory of data in a natural sample. And basically, mineral phases for any erupted rock can tell you something about what that rock experienced before it erupted. I call those the pre-eruptive conditions. So this obsidian has less than 1% sanity. It's like almost nothing. But it's got this really enormous range in composition. So this is saying orthoclase 76 to 35 means it's 76% of the potassium end member to 35% of the potassium end member. So this is a 40 mole percent range. Okay, this is a wide range in composition for a crystal. And notice there's like almost no crystals in the sample. And then the last sort of observation is that there are sparse large crystals. Now, the first and the third observation, these provide me with kinetic clues. And when I say kinetic, this means rate of reaction. And crystallization kinetics, you think of it, if I tell you a sample has 10% crystallinity, and there is one single crystal that is 10%, that might look very different than 10,000 crystals, right, at smaller mass or smaller volume. So the differences in how a sample crystallizes tells us about kinetics. And then this range in composition can tell us something about pre-eruptive path. So I got this figure from a paper. This is from Metz and Hood, 1991. And I didn't believe it at first. I said, oh, could be picking up some xenocrystals, because this is way too large of a range to find in a single sample that's almost crystal-free. So Ben Andrews, my postdoc advisor, and I went and we got on the microprobe and we analyzed these crystals. So here is a BSE image. This is a thin section, and then this is a background electron image. So this is just electrons bouncing off the sample. What you're seeing is different, the heaviness of the atomic elements here. So these little bright guys are oxides, or maybe aluminum, because I'm a terrible sample prep person, I don't know. And what you see is this like peppermint looking thing. That's what I thought was who I am. So here, I'll outline the crystal for you. There it is. It's got some nice facets on it. It's got this really crazy texture. The Sanity, the potassium-rich guy, is there. The quartz is there. There's a little bit of plagioclase right here, and then around it is this sort of halo that's depleted in the atomic components that form the Sanity. So pretty good evidence, right? You can see the Sanity crystal sucking what it needs to build itself out of the melt, and that this thing's growing. And then we mapped it with this cool technique using a high-resolution SEM. And what you can see, so here's mole percent orthoclase. So in the middle where it's bright red, we're really enriched in the potassium end member. And as you go to these cooler colors, it means that your Sanity composition is changing. So it's getting more and more sodic. And so we agreed with those results I showed you before. And so our question was, how is it possible to grow such a large ranging composition despite such low overall crystallinity? I think that's a valid question. How did this happen? And that means we need to understand something about the controls on the Sanity composition. So this means we had to do some experiments. So this is a picture of some experimental vessels. I know that you guys have an experimental apparatus here. That's what I spent my afternoon doing. It was very exciting. Great trip. And how this works is these open like clamshells, and then in the middle there's a vessel, and these can go up to 1,000 degrees C, and they can go up to like 500 bars. So let's say you find a rock that you find super interesting on one of your field trips, and you want to know where those crystals grew. Well, you put it in a gold capsule, whatever that rock is. So here's your gold capsule. There's a pen for scale. You put in a gold capsule, and you throw it in the vessel. It's like an easy bake oven. And then you cook it, and then you open up your capsule and you see what you grew. And so we ran a whole bunch of these experiments on the glass mountain lavas. And so here's our grid. So this is temperature on the bottom and pressure. We could pressurize our system to here. And so you know, I know some of you do research. I'm building one of these apparatuses at Sonoma State. So if you're ever like, man, I really want to run an experiment, please send me an email. I'm happy. Love experiments. And then each one of these red dots, this is a gold capsule with some water and glass mountain rock in it. And here's what we grew. So these lines are called phase-in curves, and if your experiment plots below the phase-in curve, it will have those mineral phases. So this experiment plots below the pink curve. It means it has Sanity and quartz. This experiment plots below the plagioclase curve. This experiment has plagioclase and Sanity and quartz. Does that make sense? So anything beneath the phase-in curve for Sanity and quartz, we can use all of these experiments to sort of figure out what are the effects of temperature and water content on the mineral Sanity. So I want to show you those. So here's temperature, and there's water content. I'm just going to plot these Sanity compositions we grew in the experiments. So all of these blue squares, these are going to be these little gold capsules, and then I measured the crystals we grew with the microprobe. And so all of these blue squares have less than Sanity crystals with less than 60 mole percent orthoclase. So these are really sodic. So here's the next set. Again, these are all experiments that have Sanity was 60 to 65% orthoclase. And then here, 65 to 69%, and then greater than or equal to 70%. And so this plot, all by separating out our experiments by composition, this plot can tell us something about how temperature and water content affect sanity and composition. And I know some of you asked me about the pelagically hygrometer. It works in almost the same way. So, to see what the effect of sanity or temperature is on sanity composition, we want to pick a water content and then move your hand across the screen. So if we pick 4.5 weight percent water and we see what happens to sanity composition as we cool down, you can see that we go from potassic compositions to really sodic compositions, right? We go from warm colors to cool colors. So we're going from potassium-rich to potassium-poor crystals. We can do the same thing. And so we learned from these experiments that lower temperatures decrease the mole fraction orthoclase in the crystal. And then we can do the same thing. What's the effect of water content? Well, let's pick a temperature, say 700 degrees, and we can see how water content the changing water content affects sanity composition. So water does the exact same thing. So as we decrease water contents, we also decrease the mole fraction orthoclase in sanity. So the whole point of this is we're trying to figure out what's causing the range of compositions in the glass mountain samples. Is it temperature? Is it water? So here's the entire range of temperatures on Glass Mountain. So it's about a 30 degrees C range. And so here, this is exactly the range from the natural samples. And you can see that this range corresponds to blue to green, or green to yellow, or yellow to red. So if we only use cooling to make that sanity, we can only move that composition by about 10 mole percent. Our natural sample had 40 mole percent variation, right? So we instead think that what happened is if you degas from 6.5 to 4.5 weight percent, you can change your composition a whole bunch. So water, for our natural samples, degassing can have a greater effect on sanity composition than cooling. So if we are thinking about our natural samples, what happened? It's likely that they ascended and they started degassing and they started crystallizing while degassing was happening. So for our pre-eruptive history, those experiments told us that this entire range of composition, which I didn't think was real, and then the sample told me otherwise, we could produce that if we just crystallized while the sample was degassing. That's all it took. So we've checked off that. So now we're left with 1% sanity in sparse large crystals. So how about you guys? Can anyone tell me, how do you make a big crystal?
Could you define large?
Large.
For this?
Millimeter.
Okay.
Millimeter. That's what we're doing.
Okay.
It's like a crystal of my dreams. Good. Millimeter. I know, low goals. Yeah, what do you think? Slow cooling? Yeah, slow cooling. I feel like we're often told that, right? So that's what I thought. Okay, so that was my hypothesis, right? And then I started reading these papers on crystallization kinetics. And I've been seeing these figures from Lofgren 1974 and Fed 1977. If you're in the petrology class or maybe even doing research, you might have seen these before. He grew these great crystals. I would say great crystals. It's all relative, right? These are great crystals. For reference, this is what it is. So these fabulous textures. And what happens is the crystal grows so rapidly, it grows along the C-axis, and so it shoots up and then it closes off. It's called hopper texture. And there's melt hollows in the middle. So you might see a great melt inclusion if you saw this in a natural sample. So I've been seeing this for years as like a reference for textures, and I didn't bother to read the scale, which is really embarrassing. So here I am as a postdoc at the Smithsonian, like, oh, look at the scale bar. And what I realized is that Gary Lofgren and Fenn, 1977, grew crystals that were about 1 millimeter or greater in 60 hours, right? So 60 hours, that's like, 3 days, right? Less than 3 days. So that's really quick to grow a millimeter-sized crystal. We think of crystals being big, or maybe you see these giant samples of mineralogy, but this is actually not a lot of time to grow something that's pretty big. You can see it with your eye. And so we wanted to test these two things. So this is sort of dogma, right? We've been told this is sort of what we think, and then here's something that we can test with our experiments. So we wanted to run experiments to replicate the natural samples. So this requires us to run continuous decompressions, and we want to make sure we're comparing apples and apples, not apples and convertibles. So we want to make sure we're comparing experiments at the same final pressure. So we want to make sure we're keeping things the same. In experiment 1, we're going to start with crystals present. So this is like a magma chamber, right? It's slow cooling. You have crystals, they just take a long time to grow. And if you have seeds, it should be easier. And up here, we started that second hypothesis, where you start with no crystals present, and you just sort of drop it to the conditions you want and see what happens. I also just want to remind you, we're using continuous decompression experiments because we hypothesized, based on all that stuff I was talking about before, that Sanity is screwed during degassing. So it's important we use decompression and not cooling. So this is important for our study. So here's the first experiment we ran. We're trying to replicate that magma chamber thing. So we're starting, and again, remember our sample has 1% crystals, so we don't want to start too far below the liquid, so we want to start just there. And then we're going to slowly decompress it to a final condition where we stop it, we pull the experiment out, and we quench it. And here's what that might look like in a time pressure pathway. And here, for reference, is the Plagioclase curve. So experiment 1, we're going to start it, right? We're going to hold it for a period of time below the Plagioclase curve. This, again, is trying to think about our magma chamber scenario. We're cool, we're having a lot of time for crystallization to occur, and then we're going to decompress it. And then our second experiment, we're going to hold it at a superliquidus position, again, above the liquidus. And then we're going to decompress it to the same final condition. So here's experiment 2. We did a hold above the liquidus to make sure we didn't have anything in there. It was just melt. And then we decompressed it to the same final condition. So again, we're trying to have these paths be similar, with the only difference being up here, below the liquidus, above the liquidus, our magma chamber and our Gary-Lofgren experiments. And the rate, I'll point out, or we're using Obsidian, it erupts effusively. We were trying to go for 1, almost made it. It was 0.8 MPa per hour. So, and that's roughly 60 meters per hour. So, who runs? I want to know who runs. Does anybody go for a run, even if it's like a sad run? No? No? Yeah, okay, sad run, yeah. I'm like I have a pace I like where I call it the beer and the crab cake pace, where if I go faster, I make a fist, it's not good. But this pace, right, we talk about this, 60 meters per hour. It would take you longer than an hour to walk a football field. So you are like outrunning the magma, right? Anytime you go for a run and you're like picking your legs up, you're outrunning the rates that we used here. So this is really slow. So I was thinking we should crystallize. So here's what happened in experiment 1. So again, below the liquidus, we're simulating our magma chamber. This is a bad day. We grew lots of little crystals. Okay, so here's what you're looking at, another electron microscope. This is epoxy. This gray color is glass. And you see these things that look like sprinkles? They're like light gray. These are all little crystals, and the average size was 30 microns. So I was like, it was a bad day. And what I learned a very valuable lesson, that my experiment didn't work, perseverance is great, but I learned that if you decompress, right, and we need to decompress because we're growing crystals that record a change of water content. If you decompress from a magma chamber, you get extensive crystallization of small crystals. It was awful and also consistent with the literature. I got my face. So what I learned is that this is not a great way to grow sparse large crystals. That is like check. That didn't do it. Now if we compare it to our natural samples, we have glass. There's no microlite crystallization, so we have sparse large crystals, right? So experiment number 2, we started above the liquidus, cooled down to the same pressure. Here's what we grew. We grew a gigantic plagioclase. So here's the scale, 50 micron. This thing's like 300 microns long. You could see it with your eye. That was a good thing. So this is decompression. This is what we learned of a water-saturated melt for superliquidus conditions, no nucleation sites. This is how you make a phenocryst. So if you want to grow phenocryst in erupting rock, you start without any crystals. For people doing experimental projects here, if you need a crystal big enough to analyze, this is a great way to grow a big crystal. And so what I learned from these 2 experiments is that the way a melt crystallizes, the kinetics, directly reflects the pre-crystallization conditions. So that is super versus subliquidus. So one conclusion was that abundant nucleation sites facilitated extensive crystallization. That was what we learned from experiment 1. In experiment 2, I learned that an absence of nucleation sites prevents extensive crystallization and facilitates the growth of large phenocrysts. And so from there, we can assign the conditions for an aplite is more like experiment 1, or your magma chamber scenario, because the aplite doesn't have any problem crystallizing. And for experiment number 2, this is more like the obsidian. This is a way you can get large crystals in the this is a way you get large crystals growing without having this microlite that will cause it to choke. So if we go back to our phase diagram from way back, we know aplites are formed as interstitial melts of granitoids, and that's from the Alan Glaser study from the rare earth element patterns. And so this means quartz, 2 feldspars, and a fluid phase. So that puts us sort of right here on his liquidus. And the second that that aplite decompresses or tries to get out, tries to escape, it tries to erupt, right? It goes towards the surface, down in this case. It will absolutely crystallize and freeze. And this is because crystallization occurs on all of the available nucleation sites. There's no kinetics, there's no kinetic problem, there's no kinetic barrier to crystallization. So that aplite's like, I'm moving, and then all of a sudden it's like, I'm approaching the solidus and I have plenty of nucleation sites to grow on. So it freezes into place. So when I ask, are the aplites freezing into place the moment they separate from their sources? Yes, absolutely. And so that's what's happening. And so when we look at this aplite dike rare earth element fingerprint, and it's not observed in the volcanic record, but it's observed in the plutonic record, it's telling us something about how these aplites formed and what was happening when they were forming. So they were around fluids and had crystals present. So for obsidians, they began, our experiments tell us, they began their life above their liquidus without crystals. But I have to ask, how does this happen in nature? And to do this, we have to look at what happens to the liquidus of a melt with like a fixed water content. And so here, and I just picked 8 for ease of figure making really at this point, but it could be 6, it could be 4, but when you move above 8 weight percent water, but you're still increasing pressure or depth, you become fluid undersaturated, and your liquidus bends over. And this is because you're missing the vapor phase. So your system, when it heats, it would rather melt. So it behaves more like a 1-bar system. And so, just as a reminder, here's a field of complete melt. Here's a field of complete crystals, and in between you have melting crystals, right? So let's say you start crystallizing at depth. You have a melt here. So you formed your obsidian melt in equilibrium with crystals, but no fluid phase. And then you move this melt up. What field is it going to move into? Is it going to move into the melt field? Yes, it'll move into the melt field. So it goes like that. So you form your obsidian melt at depth in equilibrium with crystals. You segregate that melt and you decompress it, right? We're heading towards the surface down here. And then you start hitting, so you move above the liquidus, you superheat. You reach fluid saturation, you start degassing, and then you begin degassing induced crystallization of sparse phenocrysts, right? So this is exactly what happened in our rocks, that we have sanity compositions that reflect degassing. And so kinetic lags, right? These processes that reduce crystallinity or make these sparse, isolated, large crystals, they inhibit this extensive microlite crystallization, and this facilitates eruption. So one question you could ask, I'm pointing out here that fluid undersaturation is an important part of making an obsidian. Even erupting a rhyolite, we could go further. So one question we could ask is, are rhyolites more common in tectonic settings that are not associated with large amounts of water? That's the logical conclusion. If we need fluid undersaturation to erupt rhyolites, then perhaps tectonic settings that don't have water also have large rhyolites. So a great place to look at this question is the Great Basin. So we were talking about plutons and subduction zones, right? There's fluid phases coming off the slab. So in the Great Basin, we have active extension, and it's really a semispheric upwelling, right? There's not a known common fluid contribution like there's in subduction zone. And here's a histogram of the volcanic rock compositions that are erupting in the Great Basin. Here we have our high silica rhyolites. So in the tectonic setting where you don't have abundant water or abundant fluid, you find rhyolites erupting in abundance. So this is almost great supporting evidence that water is playing a huge role in whether or not a rhyolite can erupt. And so here, just so I want to have some figures to tie this picture together, when we're thinking about how aplites form, they're going to form in the condition of melt, crystals, and fluid. So the aplites would be that red material here. The average water in arc dacites, so that upper crust unit, is 4 to 6 weight percent, and after 50 to 70% crystallization, that 4 to 6 weight percent turns into 8 to 20 weight percent. And this exceeds the solubility limit in rhyolites in the upper crust. That means you have vapor, which are the blue bubbles up there, and that's required to stabilize nucleation sites. And so as melts ascend, they freeze, and that's what prevents coalescence into plutons. So this behavior and the presence of abundant water in the upper crust prevents the coalescence of these individual aplite dikes into big plutons. That's why you don't have these huge areas. You don't go to Yosemite and say, wow, look at the giant granite pluton. Maybe you do, but that would be wrong. So you'd say, look at the granite diorite pluton, and people might roll your eyes, your friends would, we just want to climb. So be precise. All right, but for the obsidian, on the other case, I have a magma chamber down here. It could be partial melt, could be a chamber, don't care, it doesn't matter. But what you see here, we have melt and crystals, and it's deep enough so you don't have fluid. And as a melt ascends, just like we showed before, it will undergo a period of superheating, and that's because of that backbending behavior of the liquidus. And then fluid saturation, degassing happens, right? At some point in time, you do have some water present, perhaps not enough to form vapor, but as you decompress, your solubility decreases, you start forming bubbles. And then higher up, you might cross the liquidus, you start growing kinetically inhibited crystals, so large crystals that record changing meltwater contents, and eventually they erupt. And so a big takeaway from this is that magma bodies that source abundant obsidian, Long Valley, can you guys think of another place nearby that has large volumes of obsidian?
Medicine.
Yeah, Medicine Lake. So places that source abundant obsidian, Medicine Lake, those obsidians have to be coming from this type of scenario where they're coming from magma chambers that are fluid undersaturated. And that's because of that backbending liquidus. You get the interval of superheating, you can erupt a glass. And another, just taking it a little bit further, superheating might also be essential for the explosive eruption of large silicic ignimbrites. So this would be your bishop tuff and any type of rock, so monotonous dacite that have interstitial melts, thus the melt between the crystals that approaches the minimum composition. And so all of these rocks in the Andes, if we were to go way back to the beginning, we're going to shoot a histogram of the Andes compositions, so mostly dacite. All of those dacites have rhyolites, minimum rhyolites, as their interstitial melts. And so the interstitial melts might also behave the same way as the aplites, unless they're fluid undersaturated, in which case they'll erupt. So, to wrap it up, going back to our big picture of continental crust, continental crust does not develop a high silica layer because rhyolites at subduction zones, they only occur really as aplites, and they only form in the presence of a fluid phase. And this, as they erupt, extensive crystallization is triggered on abundant nucleation sites, and that causes the melts to freeze into place and prevents the coalescence of plutons in subduction zones. I should say rhyolite plutons there to be specific. And so when we look at our continental crust right here, when we're missing that felsic layer, that really high silica layer up top, the reason is for this kinetic behavior at the time of malformation. So thanks and questions. And yeah, I do have another slide for those. Yeah, thanks. And I would love questions, but I have one more just like plug while I'm email from Ben Andrews, who is at the Smithsonian. He's who I worked with on this project. And I just wanted to put a slide up while we're talking about opportunities for graduate students and opportunities for undergraduates. So I don't know who's in this room, but there's a 10-week graduate student fellowship that comes up. So if you want to use this lab and these apparatuses, and that's something you want to pursue, there's a 10-week grad program, so you can apply to that. And Ben specifically emailed me to ask me to send it to CSU, so here I am. How convenient. And then if you are an undergraduate, the museum also offers a 10-week summer program working. You could do a project like this, you could do ignite, explosive volcanism, or a variety of other things. So I'm happy to talk to you guys after that. I know there's a dinner, but I just wanted to mention it here, what was up on the board. So I would love questions. Does anybody have any questions? Yeah.
Thank you. I'm still processing it. But
Sorry.
No, that's me, not you. I was thinking though that what about I'm trying to think where I've seen large volume rhyolite isn't subduction zones, but associated with continental hotspot plumes.
Yeah.
Like say associated with
Yellowstone. Yeah.
And also in kind of late like Neo-Archean large plutons. So maybe with the hotspots, because that's still local. How would that work in coming through continental crust or right at the margin of continental crust with the fluids?
Yeah. So for that, rhyolites are common anywhere where you have basalt intruding into the upper crust. And so extension fits that criteria. But with respect to the eruptability, it would still suggest that they tend to run with lower fluids, because otherwise you'll reach the same thing that's happening to Aplites, where if you have abundant fluid phase at the time of melt formations with little bubbles and crystals also present, it will cause the melt to choke when it ascends. And so it does suggest that there's not a free vapor phase at Yellowstone. That's like, what's fascinating about this, I'm talking about crystals and melts, all of a sudden this like random fluid phase is the thing governing whether or not things erupt. So, yeah, does that help?
Yeah.
Other question? I saw like a bunch of hands. Yeah.
Between here and Sonoma State is the Clear Lake Volcanics, and you've got Mount Canocta, you've got a bunch of Obsidian. Is it the same model work there?
Slab window. So what happened there is they think there's a tear in the slab, and so there's a little bit of extension happening, or it's like this upwelling. So it's an acinospheric component. Super cool. That's like, yeah, I don't know anything about the Clear Lakes, but if it's Obsidian, same thing has to be happening.
Okay.
Yeah, I put money on it.
Yeah.
Money on it. It's good. Yeah. Yeah.
We're always told a lot about supervolcanoes being very felsic and a lot of sticky magma. But our it's a little bit off topic, but are supervolcanoes related then to this minimum temperature? I'm sorry, minimum composition.
Anytime that you
flash
huge volume of melt, yeah, that's absolutely the case. So whenever like
we don't teach that.
no, I know it's like scary because right, like you think about a huge like Yosemite-sized batholith, right? Only like granite. All it needs is a single degree C, and it's 100% liquid. Like that's a scary thing.
Yeah.
So it's those Yellowstone melts have the same property where if they are forming over time, like imagine a situation where you have Aplite dikes just forming because of fluid phase. Geology happens, time passes, right? That now becomes an extensional environment. You have all these Aplite dikes that are minimum melts, they're ready to go. If you heat them, they just move. Yeah, it's really scary. That's a great question. You're scared.
So one last question. So those experiments that you did that kind of showed time and pressure.
Yeah.
Have you looked to see, like, have you stopped those experiments all along that line to see when it was that the crystals formed?
Yes. Yeah, so that was just a small snippet of a time series. And so what we did is we did those exact experiments. We stopped it right when we thought crystals should be growing. We stopped it at 80 MPa, so change in pressure of 20, or you could think of it as a kilometer, and then another kilometer, and then another kilometer. So we did 3 different steps down. And you can, and well, what happened was any faster than that rate, outrunning the magma rate, any faster than that, nothing would grow. So it was fast enough when you started at superliquidus position. But if you ran that magma chamber, so everything would grow all the time, just like all the time. It was a bad day. I looked at those experiments. Yes.
This is a tangential question.
I love it.
What's the melting point of gold?
Ooh, 1052.
Okay. 'Cause
Degree
I know
C.
we used to talk about platinum capsules, and that's a much higher temperature.
1475.
Right. I knew there was a significant
Yeah.
difference. Okay, that's
Yeah,
good.
it's great.
So,
Oh, that's like, oh, I don't know. That's a trash.
Niobium.
That's Hannah. That's Hannah.
any other questions? Excellent. Well, let's
Thank you,
definitely
guys.
thank Dr. Waters for an excellent talk.